now I want to show you a way to visualize the entire general solution, so the entire family of solutions to a differential equation, all at once. So you saw with the um, Mathematica thing over here, you can see them one at a time by setting this bar in different positions and see different particular solutions. But how do we see them all at once? So let's see. Here's a new differential equation, and you will learn how to solve this, ones like this, pretty soon. But I don't really care about the actual solution for now. I just want to show you how you can visualize certain aspects. Actually, I'm going to go back and make some actual straight lines here. Okay, I'm back. Found the line tool. And then I didn't click out of it. So here's the space where you would plot solutions. So there are some graphs that are solutions and some graphs that are not solutions. And the general solution is going to be a whole family of graphs where each one goes with a different initial condition. Now, let me try to plot the information. Let me try to visually depict the information that's actually contained in the differential equation without solving. Because we've written the differential equation in the form x prime equals something, it's pretty straightforward to imagine what it's actually saying. So let's imagine that we have our initial condition being x of 0 equals 0. So at time 0, the state of our whatever system is, x, takes the value 0. So that means the solution is passing through here. Let me actually use a different color for the annotations here. So solution is passing through here if x is 0 at time 0. Now, when it passes through here, it passes through with a certain slope. That slope is what the differential equation is specifying. So if x is 0 and t is 0, then what's x plus t? 0. So x prime is then 0 according to the differential equation. So that means if some solution passes through here, it'll pass through with a flat or the horizontal slope. Let me actually switch to red. So if a solution passes through here, it'll pass through kind of flat. And this is all about instantaneous rate of change. So we're not saying that you've got a solution like this necessarily. We're just saying, at least in that instant that it's passing through here, it's passing through with a flat slope. Maybe it does this. Who knows? Now, I did this at the point 0, 0, but we can do it, everywhere. So at the point t equals 1, x equals 0, what would the slope be? It would be 0 plus 1, which is 1. So x prime is 1. So here's a tiny line segment of slope 1. This is, if a solution passed through here, it would have to at least instantaneously take on this slope at the moment that it passes through there. If a solution passes through here, t equals 2, x equals 0. 0 plus 2 is 2, so it would have to pass through here with slope 2. What about here? If the initial condition at x of 0 were 1, then the slope as a solution passes through there would be 1 plus 0, which is 1. So it would be like that. And let's do one more. So at 1, 1, you'd have 1 plus 1 is 2, so the slope would be 2. So x prime would be 2. So it would be something like that. Let's do another one. What about negative 1, negative 1? Then the slope would be negative 1 plus negative 1, which is negative 2. One way to fill out a whole bunch of these, I could just go through and fill in the grid, one dot at a time. But one way to fill out a whole bunch all at once is to find what are called isoclines, which are some collections of points in this xt plane where the slope takes the same value. So, for example, at 0, 0, the slope takes the value 0, right? Well, there are a whole bunch of other points where the slope takes the value 0, namely any point in the xt plane whose x and t coordinates satisfy x plus t equals 0. So all the points along here satisfy that. I shouldn't use red since I'm using red for the slopes. Let me use blue. So all the points along here, these are the points that satisfy x plus t equals 0. So this is the line x plus t equals 0. And along this line, you have always any solution that passes through any of the points on this blue line has to pass through with slope 0. So there I filled in a bunch of these. And I'm going to go to Mathematica for a second and show you a more fully filled in grid. Okay, here we are in Mathematica, where I've plotted more of these little line segments. And you can see the plot shows some of the things we found here by just filling in some of the red segments. For example, you can see that along this blue line here, you have all flat slopes. So here you have all flat slopes. And this is kind of a depiction of the differential equation as a whole. So if you want to visualize what is x prime equals x plus t, what is that saying? Well, this is what it's saying. So just to summarize and clarify, if so here the horizontal axis is t, the vertical axis is x, and any point is going to be a tx pair, a time state pair, right? So at any given point, tx, we have a certain x prime, which is going to be the slope of the graph of a solution in this plane. And that's what these little line segments are. If I'm going to have a solution to this differential equation, x prime equals x plus t, then it must, whenever it touches one of these line segments, it must touch tangently to it. So these are the slopes of the tangent line to any given solution. So just staring at this, you can imagine what the solutions look like, right? They sort of tend to flow along the little line segments you're seeing. And of course, there's not one solution that you can visualize here, but a whole family of solutions, right? So there are a whole bunch of curves. Let me try to draw on this to show you what I mean. So here's t, x, and there's going to be a whole bunch of solutions that tend to follow these curves. I don't know if what I'm drawing are exact solutions, but just, you can imagine that there are many solutions, one for each initial condition. So the picture as a whole is a picture of the general solution. And when you make one of these pictures, this is called a slope field. So a slope field is a way of visualizing the information contained in a differential equation, specifically in a first-order differential equation. That's where it helps you. If there were higher derivatives, then we wouldn't be able to make a picture like this. Okay, one more thing here. If you remember our infection model, x prime equals 3x, we can make a slope field for that, and it looks like this. So here all I've put in is the information of the differential equation. I have not put in anything to do with the solution we found. So I only had to type 3x somewhere. I don't have to put anything having to do with exponentials. And you can see that if you try to follow these curves and draw one curve that flows along these line segments, then it's going to look like an exponential growth. Kind of like like this. If I try to not so skillfully draw a curve that always is tangent, it's some kind of exponential, a curve that's always tangent to these little line segments. Okay, so the reason you're seeing that there are many kind of curves that flow along the segments is because what you're seeing is a sort of the general solution. A specific solution needs initial conditions to be pinned down. And I want to also show you what happens if I go back to thinking about, instead of just the one differential equation, x prime equals 3x, think about x prime equals rx. So let me put an r here. Then, of course, it cannot really plot anything because it doesn't know what r is, but I can create a little bar that I can manipulate r, let's say from 2 to 4. So here, if I move that bar, it's a little bit subtle, but do you see the, let me try to make the changes to r more dramatic. Do you see the slope field shifting? So each time I fix r, I'm looking at one differential equation and one family of solutions associated with that. And as I change r, I'm changing the differential equation. And so I'm changing what the general solution would be. If you fix r and you then also fix an initial condition, then there's exactly one curve, one graph to fill in here that would serve as your particular solution, x of t.